have actually talked about how we can estimate the head loss. Right? So actually the datum is arbitrary level. So you can put datum here or here, it doesn't matter. Right? It's gonna change the absolute value for the total head, but because the elevation will be compensated, so the pressure head will not be changing. Okay? The location of the datum doesn't affect the flow pressure, but it's gonna change the value in total head and the elevation head. So you can put any level as a datum. You can decide, or you can select any level as a datum, which will be the reference point. Let's put the datum at the lower level, and in that case, total head at point, let's say here's A and here's B. What's the total head? HT at B. 0. Thank you. 0 meters. Because you don't have any head loss from the lower water surface. And at the lower water surface, HT is 0, and the elevation head is 0. Here, what's the total head at point A? 8 meters. Right? And as water flows through the soil, head loss will occur gradually. And if you assume it's going to decrease linearly along with the length, then you have at some point this will be 8, 6, 4, 2, 0, so 4, maybe 2, maybe 6, right? So this way you can graphically estimate the total head. Datum in this is and what about the elevation head? If you have a section drawing, which is drawn to scale, then you can estimate also the elevation head. Right? So how big is it from the data? Here, for example, this is the HT is 2 meters, and what's the number? Maybe 4 meters. Then elevation head will be negative 6 meters. So the pressure head, how much is the pressure head? HT minus HE. So 6, sure. 2 minus 6. 8 meters. Okay? So from there you can calculate the core pressure. Right? And if you have the data for the soil density here, then you can calculate also the total stress. So that way you can calculate the effective stress. So the question, when we have this kind of a 2D flow problem, we need to have a section drawing for the water flow, and the objective of this 2D problem is to estimate the total head, pressure head, and elevation head at any given interesting point, and calculate the core pressure and effective stress. And one more thing is, in addition to this, the other question would be, what's the flow rate? For a given section, and stability of the dam. One example is that you have a water pressure profile like this, and this can slide the dam so that they move from the original position. And also you have a water pressure developed underneath the dam like this. And it may lift up the dam structure, or it may rotate the dam structure depending on where the gravity center is. So that's this is the case that we want to check, which is called dam safety or dam stability check. And all of these problems can be solved by Seepage theory. First, let's understand the Laplace equation. Laplace equation is from when you have a soil domain. So this is the final form of the Laplace equation when you have a water flow going into the soil mass and you have a water flow out coming out of the soil mass. And the soil mass is the width and the length is dx and the dy respectively. And in the 2D domain, hydraulic head here at HT is the total head, and total head in the second derivative times the permeability plus ky times the second derivative of the respective to dy is to 0. So this is the Laplace equation. So if you solve, this is a partial differential equation. If you solve this, then you will get the HT and in any xy position. For example, if you want to know the total head at this point, then you're going to put the boundary condition here and you solve this partial differential equation. Then you get the HT. So this is the governing equation that you want to solve. And if this 1D case, Kx. By the way, the Kx is the permeability in x direction, and y is the permeability in y direction. When this 1D case, dy is 0, so Kx prime if this one-dimensional problem, then the second term will go to 0. So you have only one, the first term remain, and you solve it. Then round HT over round X becomes the constant value, which is the hydraulic spread. There are several solutions. So this partial differential equation in 2D domain, which is the Laplace equation, can be solved with these kind of approaches. So first we can mathematically obtain the exact solution to solve it properly. But this can be done when you have very simple geometry only. And there's a graphical solution which is called as a flow net analysis. And this is what we are going to learn from this course. This one will be covered. And there are approximate solutions, which is kind of also the mathematical, and a numerical solution that you can solve it by computer simulation, like using finite element method or finite difference method. And so these are in the lab. Operation in technical stress and to get the flow rate and to check whether the condition is safe against the quick or fast condition. These are the three main objectives of the flow analysis. The method of flow lines and equipotential lines are called flow net. And let's go back to the original the problem where we have a dam and the upper water upstream or surface and the downstream, and you have a bedrock. Then we can draw the flow net like this. And the equipotential line will be like this one and this one. So this blue line is called the flow line. And this represents the flow channel of water. Flow of water. And this red line is called the equipotential line. So equipotential line is contours or constant total head. So this is a contour. So in this case, we have two flow lines, right? We have two flow lines, and we have 1, 2, 3, 4, 5, 6, 7 equipotential lines. What about the flow channel? Flow channel is, for example, let's say that we have a flow line like this, then flow channel is this is the flow channel. So in this figure, the flow channel, how many flow channels you have? 1, 2, 3, right? 3 flow channels. And the assumption is that you don't have any water flow across the flow line. So the water doesn't go across the flow line. So it's going to go through along the flow line, along the flow channel. That's the main assumption. So no flow occurs across the flow line. And the equipotential line is, so along this red line, for example, here you have a same total head. At this point, at this point, this point, total head is the same. Okay? What about here? Total head here, 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 or at the bottom, because it's at the same equipotential line, the total head are the same. Okay? At the water tip, also any point on the line will have the same total head. Okay? But from here to here, So from one equipotential line to the next equipotential line, you will have head loss. So total head will be dropped by delta H. And that head drop or head loss will be the same across each equipotential line. For example, from here to here, you have a 1 meter drop, and the next drop will be also the 1 meter. And after that, you have a like same interval for the head drop or head loss. Okay? So that to satisfy this assumption, we have to draw it very carefully. So there are two rules. Rule number one is to maintain the normality. That means the flow line meets the equipotential line at right angle. This is an equipotential line, and this is flow line. So always the equipotential line have to meet at right angle with the flow line. Perpendicular. And the second is maintain the square flow rate. It's like each square should have the same width and the length. When the widths are very similar, width is similar to the length, then it becomes the square flow. Actually, this handout summarizes the one I just told you in one page. So very useful. Let me read the first paragraph. The path taken by moving particles of water as they flow through a permeable material may be represented by a series of flow lines. And flow lines are nearly parallel curved lines since water tends to take the shortest path from point to point. So don't need to change direction in fluid. So when you draw the flow line, as I drew here, it's going to be like parallel to each other. And it will be very smooth, so it doesn't have any sharp edges. Okay? And the point of equal head of water, so where the total head are the same, is represented by the equipotential line here. And if each line crosses the flow line at right angle, so it will maintain the normality. And it's easier to interpret when you draw the square flow net. The pattern of the approximate polynomial squares formed by this line will have the squares, will have the similar width and length. And to construct the flow net, a cross section of the site and the structure is drawn to the scale. So you will see why this is very important. So you need to have a cross section drawing, like a CAD drawing or the hand drawing will be needed, which is drawn to scale. And then the boundary conditions are again, and flow lines start and finish at the right angle to the inlet and outlet surface. Why? Because inlet and outlet surface are also another equipotential line. And equipotential line start finish at right angle to the impermeable surface. In this case, impermeable surface will be the bottom of the bottom of the dam because it's made of concrete, and at the top layer, the surface of the bedrock, because water doesn't go in. So equipotential line will start at right angle from the beneath of the dam, and it's gonna end at that point where it meets the bedrock at the right angle. So here, right angle, right angle, right angle, right angle. And also, when they meet, if the flow line should be also close to the 90 degree. Few trial equipotential lines are then added. Okay. So first, you're gonna draw the flow line first. It's easier to draw the flow line. So you need maybe 3 or 4 flow lines are enough. 2, 3, 4. You don't need more than 5. Then you draw the flow line, and then you're gonna draw the equipotential line, keeping these two. This is unlikely to be achieved at the first attempt, so that you're going to have to adjust the equipotential line to make it square flow line and maintain the normality together. Let's look at the example here. And again, you will do this practice in the lab at the lab, and you will report it at the lab report. So first, in this case, you have a sheet pile wall that's blocking the water. So maybe inside to the excavation site, or you're going to build something inside. And here's the water. So the water will flow from where to there? Higher water level to the lower water level. So it's going to go inside from left to right. And it's symmetrical, right? It's symmetric. So you can draw, so maybe 3, here they drew 3 flow line. And then, after that, here, look at the equipotential line. Impermeable, where is the impermeable boundary? Impermeable boundary is the bottom bedrock and also the wall. Water cannot penetrate the wall. So that it starts from here and it's going to end at the bedrock, but you will maintain the normality at each intersection, and you draw it to make it square flow. You may want to draw maybe more if this one is longer to make it square. So you may need that. So if number of the equipotential line will depend on the whether you can make this structure or not.